Okay, so we are looking at special right triangles. Starting with box number 31, we have an equilateral triangle with an altitude. So we have an equilateral triangle, which means all three sides are the same length. Okay, so each of them is 2x long. You can see that this side is 2x long, this side is 2x long, and this side is 2x long. Okay, and if you use your Pythagorean theorem, which is a squared plus b squared equals c squared, c being the long side, okay, hopefully that looks familiar to you guys. A squared plus b squared equals c squared is how you can calculate the three sides of a triangle for any right triangle. Then let me fix the attendance really fast. Okay, then thank you for the reminder. Then we're plugging it in to solve for our height, which is the altitude, which is the b value, this side. If we're looking for the b value and we know that the side is 2x, the long side is 2x, then we get our b value is x radical 3. So x times root 3. Okay, so you can just remember this. They show the whole process here. We could talk about it a little bit. If x squared, oops, let me use a different color. This x squared is this yellow side right here. Ah, I did not mean to zoom out. That was a mistake. Okay. This yellow side is x, so it's x squared, plus the green side is the b, so b squared, equals the 2x squared is the hypotenuse in this little zoomed in right triangle. Okay, so we're only talking about that part, okay? This little triangle. So we're solving for the height using the Pythagorean theorem. If you plug it in like that, we have x squared plus b squared equals 4x squared. You subtract x squared on both sides so that you can cancel these out. And then you'll be left with b squared is equal to 3x squared. To get rid of the square over here, we just need to take a square root. So we square root the b squared and we square root the 3x squared, and you're left with b is equal to x radical 3. So that's how we got there. Okay. And I know that looks like really weird and random, but just follow along for now. We'll go over some example problems and hopefully it will make more sense. And then let's take a look at this triangle in box number 32. I want to show like the whole thing, but zoom in. Okay. So in box number 32, we have a 30, 60, 90 triangle. The theorem is that the length of the hypotenuse in a 30, 60, 90 triangle is 2 times the length of the short leg, and the long leg is radical 3 times the length of the short leg. So let me just recap by saying that triangle on the left that I was coloring is literally the same triangle as this one over here. So this green line that I just drew is the same as the green line I drew over there. That's the B, which we said was x radical 3. This yellow on the bottom is the same as the yellow on the bottom over there. It's just the length is x. We're just kind of focusing in on this little triangle that we cut out of our equilateral. And over here we have 2x, which is the same as the blue side over there. So we're just zooming in onto this particular triangle, which is half of an equilateral. And this is a special right triangle because it's going to come up a lot in math. It's got 30 degrees, 60 degrees, and 90 degrees as the angles. So here's your 30 degrees, here's your 60, and then your 90 is represented by that right angle over there, the square, the right angle. So the long leg, that's the green one, okay? The long leg is equal to the short leg times radical 3. The short leg, you can use these formulas to help you solve for it, is equal to the long leg divided by radical 3, which is also the same thing as the long leg times radical 3 over 3. okay? And then the hypotenuse is 2 times the short leg, and the short leg is half of the hypotenuse. Okay, so I know that this looks like really wild right now because it's just so many x's and radicals and you're just like, oh my god, what's happening? So let me just give you like a really quick example with a 30, 60, 90 triangle that I will draw over here to the best of my ability. That's not that bad, is it? Okay, so here's my little mini 30, 60, 90 triangle. This is your x side. This is your hypotenuse side. Sorry, I don't know why I said x side. X radical 3 side. This is your hypotenuse, and this is your x side, the bottom. So if the bottom is, let's just say 5, just came up with a random number, it's just an example. I'm probably lagging because I see that my image is not caught up to what I'm actually writing, so I'll wait. Please don't disconnect. Oh my god, okay, so I probably lagged a lot. I just wanted to draw you an example, okay, so that's what I was doing. So I labeled it 5 on the bottom just to give you some examples. So this x is the 5, okay? So then the green side would be 5 radical 3. And then the blue side would be 2 times 5, which is 10. Okay, so here's just a little example for you in numbers. Okay, so that was the first 2 boxes. Do you guys have a question on those boxes? Okay, maybe you will later on when we do some example problems, but just keep those equations in mind and we'll get back to them when we use them. We'll get back to them when we use them. Let's go to box number 33, square with a diagonal. So we're going to derive another special right triangle, this time using a square as our starting point. So we start off with a square, and then let's highlight the different points that you have. So your hypotenuse is over here, it's your C. Let me make it look a little cleaner. Okay, so here's our hypotenuse, and then we have our 2 legs, which, since it's a square, they are equal, they are congruent. So then when you're plugging it into our Pythagorean theorem, which is a squared plus b squared equals c squared, you get x squared plus x squared equals c squared, c being the hypotenuse. And let's solve for c, because it's the one side we don't know. So x squared plus x squared is 2x squared equals c squared. Then we square root everything to get rid of the square, and you're left with x radical 2 equals c. So I'm going to put a little box around that one. Our c value is x radical 2. Now let's zoom in specifically onto that triangle. Though they rotated it this time, it's okay. It's still the same triangle. Don't know why we rotated it, but see, here's our x. The 2 purple sides are still those 2 same purple sides. And this is our hypotenuse, which we determined was x radical 2. Okay. So the hypotenuse, which is the blue side, x radical 2, is equal to the leg, which is the purple side, times radical 2. And then the leg itself is equal to the hypotenuse divided by radical 2, also known as the hypotenuse times radical 2 divided by 2. Okay, so you can use either of those formulas depending on which one helps you more in the situation. So let's give you another example right over here, my somewhat ugly best attempt at a 45, 45, 90 triangle. Why do they look like that? There you go, that's a little better. Whatever, good enough. So here's my like little 45, 45, 90 triangle. Let me color it in. That's not coloring. There we go. Okay, so then if we come up with any random old number, like 5 again, because I'm not being creative right now, we'll wait for my computer to stop lagging, my internet to stop lagging, hopefully. Okay, so there's my 5. I'm just giving you an example with numbers. Then the other side will also be 5. Our two legs are the same in a 45, 45, 90 triangle. It says my internet connection is unstable, so that means you didn't hear me probably. What I was trying to say was that if one leg is 5, then the other leg is 5 because we have a 45, 45, 90 right triangle, which means the two legs are the same. The two legs are congruent. And so finally for the hypotenuse, it's 5 radical 2. We literally just write it as a number and then put the radical 2 next to it. Okay, so we'll get into some examples for those later, but for now, does anybody have questions on the boxes 33 and 34? Alrighty, interrupt me if you do, but let's go on to the last box, which is box number 35. We got an isosceles, triangle, and altitude. So just to remind you guys, an isosceles triangle is where you have two sides that are congruent. So in this case, this one and this one are congruent, okay? And this third side on the bottom is not congruent to our other two legs. So this is our isosceles. And then if you take the altitude of your isosceles, meaning the height, like when you fold it right in its line of symmetry, so you fold it right over here on this dotted line, because this is what would make it symmetrical. If you actually had your triangle on a piece of paper and you wanted to fold it in half, this is the way you would fold it, so it folds onto itself. This is the line of symmetry. That line of symmetry is your altitude. It bisects the vertex angle and it bisects the base. So this is your vertex angle. Okay, it's lagging, so I'll say that again when I see my image reappear. Okay, so that dot at B, so I'm trying to emphasize that that angle is your vertex angle. So it bisects it, meaning that the angle B got cut in half, okay? So this angle is the same measure as this angle because angle B got cut in half. That's what it means right here. And it also bisects the base. So the base is this one on the bottom. So the green line cut our base in half. So this section, which ends where the green line is congruent to this section. Okay, so that's what it means by bisects the base. Do you have any questions on that one? All right, so that's it for our notes. I'm going to stop recording.